Okay, ladies and gentlemen, this is the video for the supplemental Chapter 7 periodic table notes. We're going to be talking about basic parts of the periodic table, properties that go along with those parts of the periodic table, and then some key reactions of certain groups on the periodic table. So first up, fundamental parts of the periodic table. As you know, the elements are all divided into metals, nonmetals, and metalloids. Metals, on the left side of the periodic table, they will lose electrons. They have the lowest ionization energies of the elements on the periodic table. That's why they lose electrons, because they have low ionization energies, because it is, relatively speaking, easy to remove the electrons from a metal. Nonmetals, on the other hand, have a tendency to gain electrons until they have a full p sublevel. So they are trying to fill up their SNP, get to that stable octet. They're interested in gaining electrons in order to do that. Because of that, they have the most negative electron affinities of elements on the periodic table. And what I mean when I say most negative electron affinities is that the nonmetals release the most amount of energy when you add an electron to them, because electron affinity, energy change associated with adding an electron, the nonmetals will release energy when that happens. They have negative electron affinities, so they're giving off energy. They're becoming more stable when you add an electron to them. Metals. When we talk about metallic characteristics, what it means to be a metal in terms of properties, in terms of behavior, we say that the most metallic metals are in the lower left-hand corner of the periodic table. Essentially, when Mrs. Julian thinks what it means to be a metal, the first thing that comes to her mind is the ability to lose electrons. And of all the metals, the one that is most likely to lose an electron is cesium. It's in the lower left-hand corner. It's going to have an extraordinarily low ionization energy. So basically, the closer we get to cesium, the more metallic our metal becomes. The more the things that we think of when we think of metals, those properties increase the closer we get to cesium. Properties of metals: luster. They are shiny. Metals conduct heat and electricity. They are malleable. They are ductile. They are mostly solids at room temperature, with one exception, and that's mercury. Mercury is a liquid at room temperature. But these are the basic properties of metals. We're going to return to some of these properties a little bit later in our bonding slash intermolecular forces unit, because part of this reason why they do all these things is related to, if you want to call it either bonding or IMFs. When we're talking about metals, it gets a little hazy where that line between them is drawn. Nonmetals, properties of nonmetals. The most nonmetallic characteristics are in the upper right-hand corner of the periodic table, but we are excluding the noble gases when we talk about upper right-hand corner. When I say upper right-hand corner of the periodic table, for the most part, 99% of the time, I'm actually going to be referring to fluorine and not helium, due to the relative inactivity of the noble gases. Because nonmetals, what do nonmetals have a tendency to do? They have a tendency to gain electrons. So what is the best at attracting an electron to itself? Fluorine. So electronegativity. Nonmetals, properties of nonmetals. They are dull. They don't have luster. They're not shiny. They are very poor conductors. They have lower melting points than, typically speaking, than the metals. But there's also a large variety in the properties, which we can see through this lower melting point thing, because nonmetals, there are nonmetals that are solids, there are nonmetals that are liquids, there are nonmetals that are gases at room temperature. Whereas all of the metals, save for one, are solids at room temperature. Nonmetals, we got all three. We got elements like carbon and phosphorus and sulfur that are solids at room temperature. We got bromine, which is a liquid at room temperature, and then we have gases at room temperature, lots of gases. Nitrogen, chlorine, all the noble gases, oxygen, fluorine. The metalloids separate the two. They're the stair step in the periodic table. The big thing that you need to remember, though, is that aluminum is most definitely a metal. Aluminum is in contact with that stair step boundary, but it is not a metalloid. It is definitely a metal. It's the only little exception there. Their properties are a combination of the two, metal versus non-metal, and they have a tendency to alter their properties based on what you're pairing them up with. I will add that for the purposes of our discussion of bonding, which is coming up next, when we see a metalloid in a compound, we're going to treat it for the most part like a non-metal. So most of the time when we see a metalloid, we'll treat it like a non-metal. We'll assume it's behaving like a non-metal. Properties about metalloids, big one that I do want to point out, semiconductors, silicon, huge in technology. The alkali metals, group 1. So talking about some groups specifically now, I do want to make sure we are very, very clear. Hydrogen is not an alkali metal. Hydrogen, for the most part, behaves as a non-metal. This discussion does not have to do with hydrogen. As we're moving down the group 1 alkali metals, we will always see, we tend to see these two patterns, a decrease in ionization energy. Ionization energy is getting smaller. That means that it's getting easier to remove the outermost electron. It takes less energy to do that. The reason is because our atomic radius is increasing as we go down a group, because we are adding on additional electron energy levels, and therefore because the atomic radius is increasing, our nucleus is not holding on to that outermost electron as tightly as possible, making it easier to remove it. We also see a decrease in melting point. And alkali metals behave as reducing agents, which mean that they oxidize very, very easily, because a reducing agent is something that causes something else to reduce, right? A travel agent doesn't actually travel with you, they simply help you travel. So a reducing agent helps something else to be reduced, meaning that they themselves are oxidized, meaning that they themselves lose electrons very, very easily. So this is saying that if you put an alkali metal with something else, the alkali metal will probably force the something else to be reduced because it itself is so interested in being oxidized. And that's precisely what happens when we put alkali metals together in water. This is a not good combination. There's a reason that we don't make jewelry out of the alkali metals, because they are so reactive that they would react with the water that is in our skin, and then, bad things would happen. When alkali metals react with water, they form hydrogen gas and metal hydroxides, alkali metal hydroxides. So we're making hydrogen gas, which, as you told me in class, is flammable. And then we're making a metal hydroxide, alkali metal hydroxide. This is a group 1 hydroxide, so we're making a strong base. I mean, look at the products of this reaction. Flammable gas, strong base. These are not safe products. This is a chemical reaction that's producing some fairly unsafe stuff. And I do want to remind you that when we're talking about water here, you can probably see that this is a single replacement reaction. Single replacement. So water, what I want to point out is that when water is involved in this single replacement reaction, we replace one of the hydrogens. It's just one of the hydrogens that's being split. So whenever we've got a reaction with water, water doesn't lose both hydrogens at the same time. Water is composed of the hydroxide ion and the hydrogen ion combined. And when it splits, it's going to split into those two things. So it splits to get this hydrogen will be forming the H2 gas, and then the hydroxide makes the metal hydroxide that we're left with. So that's how water splits. It splits into the hydrogen ion and the hydroxide ion. An example of this with sodium, you've got 2Na plus 2H2O makes 2NaOH plus H2 gas. The coefficients, they're there for balancing purposes, recognizing that when we split that water and we get that hydroxide, hydroxide has a +1 charge. When sodium has a charge, it's also +1, so we're just making sure that everything is balanced out. These reactions are highly exothermic. They are giving off heat, and they give off so much heat that it is possible to ignite the hydrogen gas gas that is being produced. And that's what we see when we do see a spark or a flame, as you did with the potassium in class. It's giving off so much heat that's actually igniting the hydrogen gas while it's being produced. Which alkali metal reaction is going to be the most exothermic? It's going to be the one that's most reactive, the one that has the lowest ionization energy. So this is going to be cesium. And recall, and if you're at this point you're saying, but Mrs. Julian, there's an alkali metal beneath cesium. I'll remind you that francium is highly radioactive and it has a half-life on the order of seconds. So this means that we haven't been able to study francium to confirm that it is in fact more reactive than cesium. We think it is. We're fairly certain it would be, but this hasn't been tested. So when we talk about the alkali metals, we really are referring to simply lithium, sodium, potassium, rubidium, cesium. 5 of them. Francium, we just don't know. We're not sure. We can't confirm it. Alkaline earth metals. So we're moving on to group 2. Now group 2, beryllium, magnesium, calcium, strontium, barium, radium, they are not as, all of them are as reactive as group 1 elements, but they are still pretty darn reactive metals. When I think about reactive metals, I really am thinking group 1, and for the most part group 2. To show you what I mean, not all as reactive as group 1 elements. You put beryllium in water, nothing's going to happen. You put magnesium in water, you will get a slight reaction, and it is a slight reaction, but it's definitely a reaction. I mean, you put magnesium in water and you put in, you'll be able to see eventually that things are changing. Calcium and below though, calcium and lower, so calcium, strontium, barium, you put them in water, you're definitely going to see a reaction. So it's that whole ionization energy trend again. Ionization energy decreases going down a group, making it easier to remove that outermost electron. We see a big impact with this with group 2 in their reactivity with water. Now, calcium and below, when they react with water, they're going to react, notice, in the exact same way. We're still producing a hydroxide and we're still producing hydrogen gas. The only thing that has changed is the balancing. And the only reason that that has changed is because group 2 ions will have a +2 charge. So we need to have 2 hydroxides balanced with them, but it's still the exact same reaction. We're making a hydroxide and hydrogen gas, and so this is just showing you the specific reaction when you put calcium in water, and this will happen. This is reactive. It's definitely a reaction. You're going to see stuff. You're going to see the hydrogen gas being given off, but it doesn't happen to quite the extent that the group 1 metals react. You are not guaranteed a flame. It's not necessarily that exothermic. Hydrogen, just to comment on hydrogen. Hydrogen is truly a little anomaly on the periodic table. For our purposes, we're going to lump it in with the nonmetals. We put it in group 1, however, because it's got that 1 valence electron. So there are some similarities. It's sort of tough to really nail down what hydrogen does, and things get especially weird when hydrogen just loses its single electron, because then it's just a floating proton. The most common isotope of hydrogen has no neutron at all. It's just H1. So it's just this little floating proton around that's highly reactive, because that's what acids are. It's right, H+. So hydrogen is this little bizarro element on the periodic table. We're considering it a nonmetal for our purposes, but we put it with group 1, doesn't really act like group 1. Thing is though, if you react hydrogen with metals, if you take hydrogen, you react with metals, then it's definitely going to behave like a nonmetal, and it'll react to form metal hydrides. And this is the case where hydrogen's oxidation number is not automatically +1. If you look at oxidation numbers here in this reaction, a metal plus hydrogen making a metal hydride, the metal is 0, hydrogen gas is 0, right? Elements by themselves when they're uncombined are 0. We don't have charges on the sodium, we don't have charges on the hydrogen, so there's 0 here. When we look at the product, sodium hydride, the sodium is +1. Because it's sodium, it loses its electrons. It's behaving as a reducing agent. And it forced its electron onto the hydrogen, so the hydrogen is -1. This is the case when hydrogen is not +1. Hydrogen is -1. Allotrope, a new vocab word. Allotrope is a term used to refer to elements that are the same as one another, but coming in different forms of the same element in the same state. Oxygen and sulfur are good examples of this. When you find oxygen out in nature, you will find it as either one of two forms. Oxygen comes in either the O2 variety, which is the most common variety out there, but it also comes in O3 flavor. You can get your oxygen as either O2 or O3, as either oxygen gas that we breathe or ozone, O3. And these two things are what we call allotropes. O2 and O3, they are allotropes of one another. They're allotropes because they're the same element. It's just oxygen. This is not compounds that we're talking about. This is periodic table, so we're considering the elements on their own. They're the same. They're the same element. They're both oxygen, but they're coming in different forms. So they are allotropes. So O2, O3, these are allotropes of one another. Sulfur has many different allotropes. Sulfur is found in many different forms. S8 is the most common allotrope of sulfur. There's also S4. There's also, I think, like an S30 or something like that. All the sulfur sort of coming together in a very strange way. Buckminster fullerene, C60, 60 carbon atoms bonded together in a soccer ball formation, is an allotrope of carbon. It's a flavor that we find carbon in. Diamond could be considered an allotrope of carbon. It's a way that we find carbon. So allotrope simply means different ways that you can find the same element in nature. Best example is really O2 and O3. They're different forms. They're two different things. They will react differently. Ozone does not react the same way as O2 does. Because its bonding is different. Halogens, group 7 or 17. When I was in school, we called it group 7. Now it's called group 17. But whatever, I'm over it. So if I ever say group 7, no, I'm talking about the halogens. Halogens have extraordinarily high electron affinities. And when I say high electron affinities, I mean a negative number that is large in magnitude. I mean that they will release a large amount of energy when you add an electron to them. So to be very clear, that's what I mean when I'm saying a high electron affinity, a large negative number. Fluorine in the halogens is the most reactive element on the periodic table. It's got the highest electronegativity. It's capable of removing electrons from pretty much anything. You put fluorine in glass, you no longer have glass. Give it a little while, you will have what used to be glass because the fluorine removed the electrons from the glass. It's that reactive. You have to store fluorine and fluorine compounds in plastic. It won't react with the plastic. Halogens react with hydrogen to make acids. If you put hydrogen gas and a halogen together, you will get what will become an acid. You will get this 2HX gas. So this X stands for any halogen. But when I will add that in order to actually get this this product so that it donates a proton, you will have to then bubble that gas through water. It has to be aqueous. So you react a halogen with hydrogen gas, you will get a gas that can then later become an acid when you put it in water. Noble gases. The noble gases, group 18, they are stable, they are monatomic, they have completely filled S&P sublevels, they're hitting the octet rule nicely. Every other element on the periodic table is trying to be like the noble gases. We used to call the noble gases the inert gases. That used to be the name for group 18. Until 1962, when we had to change the name of it because it turned out that you could get the noble gases to react. But they're only under extreme circumstances, and so this isn't done normally. They will not react on their own. You really have to force them to react. Your book says that your book says that only xenon and krypton have formed compounds. That is no longer the case. All of the noble gases have been reacted. They have formed compounds with all of them. Helium was the very last noble gas that we got to react. It wasn't until 1998, which in terms of chemistry is actually pretty recent. Chemistry, not too much has changed in the fundamentals of chemistry in the last 30 years or so, which is why we don't really need a new textbook. It's okay if it's got this one like slight anomaly. Helium was the very last one to get to react. Why was it the last one? Think about ionization energy, think about reactivity. Helium, it's so small. It's holding on to its electrons super tightly. It's not going to be interested in sharing them. Its radius is tiny. It's going to be least reactive. Why did they react it with fluorine? Simple. Fluorine's the most reactive element on the periodic table. You're trying to get something to react that doesn't want to react. You don't want to pair it up with something else that doesn't want to react. Otherwise, you're never going to get a reaction. You want to take something that you don't think is going to get to react with something that's crazy reactive, because that's your best shot at forcing this thing to do something. So HEF2 was kind of the final straw in terms of the noble gases. The last one, we finally got the helium to react, and that's why we no longer call them the inert gases. We have to call them the noble gases, because it's not true. They are not completely inert. You can get them to react, just not easily. So that is the end of the supplemental material from chapter 7. You are responsible for this information, but as I said, we don't need to talk about it in class.